Greetings! Welcome to Electronics2. This is lecture number 6 and I am Razavi. Today we will continue to look at current meters and explore some of their interesting properties. In particular, we will go over some examples of current meters and just get comfortable with this topology. And then we'll talk about a different way of thinking about how a current meter operates as opposed to what we did last time. And then talk about the proper scaling within a current meter to make sure that the currents match reasonably well. And then we will extend these ideas to bipolar current meters as well. All right, but before we go there, let's look at what we covered last time. So here's a quick summary. So last time we said here's the problem that we face in many circuit designs. We have a golden current source. Now this is not standard terminology, it's just the word I am using. A golden current source meaning one that is very stable, it's not very temperature and supply dependent. And I would like to make many copies of this current source because I need many current sources, tens, maybe hundreds of current sources in a given circuit. So how do I do that? I have some sort of black box that receives this golden current source and in return generates these. So we have to see how this information is transferred from this current source to these current sources so that these are as good as this or almost as good as this. Okay, so then we took a step back and just started playing with some devices. In particular, we took a diode connected Mosfet, which means its gate and drain are shorted, and simply injected a current between these two terminals and tried to find the voltage between these two. So this is a large signal test where this current goes from 0 to a large value, and we are trying to plot V1. And based on the original equation that we have, which relates the current to the voltage, we needed to find the voltage in response to the current. So that's the voltage that we measure across the device. Okay, so that in particular is not that interesting. But then we said, okay, let's go one step further and try to take this VGS that this device has generated from this current and give it to another transistor, assuming that that transistor also is in saturation. So then we went ahead and found the current flowing through this device, and we saw that that current and this current are related by a nice simple ratio. So if I1 is a good constant supply and temperature independent current source, then so is I2. And that was the basic idea behind the current mirror. So then we drew the current mirror like this, where we have a reference current. Again, that's the golden current source that is injected into this diode connected device to generate a certain VGS. And then this VGS is applied to a destination or a copy. This becomes a copy of this current source, right? And we see that now we generate a current that is Iref times this ratio. Okay, so if I want I2, for example, to be equal to Iref, I simply make these two identical. So M2 and M1 will be identical transistors, and then I can copy this. All right, so let's go over some examples of playing with current meters, just so that we are more comfortable with these things. So, okay, suppose that we have a circuit includes two source followers biased at 100 microamps and 200 microamps. Okay, so how do I generate these currents? We have a reference current, a reference current of 50 microamps. Okay, so we have an Iref equal to 50 microamps, and we would like to create two current sources to bias these source followers. So here's the situation. I have a source follower here. Remember, source follower is a stage that receives the signal at its gate and generates the output at its source, and is preferably biased by a current source on the bottom. So we need a current source here. That's one, and then we have another one. We have two of these. So this guy needs 100 microamps. Now we go to another one. This is the second source follower, and this guy needs 200 microamps. Okay, sorry, I have to draw that as an NMOS device so that I don't have to redraw it. Okay, so here's an NMOS device. Okay, now I have a reference of 50 microamps, so that's 50 microamps. And I need to copy this onto here and onto here to create 100 microamps and 200 microamps. All right, so first we pass this current through a diode connected device, like so. So pass this current through a diode connected device. Let's call this M1. We call this M2 and this M3. This diode connected device, in response to this current, generates a certain VGS. Now it just happens that VGS and VDS are equal. Okay, so it generates a certain VGS. And going to apply that VGS to the destination current sources. Just the way I apply this VGS to M2, I'm going to apply that to this M2. So these two have the same VGS because their gates are shorted, and so are their sources. The sources are grounded. Okay, so how do I get 100 microamps from 50 microamps? Well, we know that this current is equal to this current times the ratio of the W over L's of the transistors. So all I need to do is pick W over L of 2 to be equal to 2 times W over L of 1. And then this current will be twice as much as this current. Okay, how about M3? Well, M3 follows the same idea. We have a VGS here produced by M1 in response to 50 microamps. I'm going to take this VGS and bring it here. So I just need to connect this gate over here. So again, M1 and M3 have the same VGS because their gates are shorted and so are their sources. So M3 follows the same principle. So in this case, we just have to pick W over L of 3 to be 3 times WL over L of 1. Then this ratio is 3, so we copy the current by a factor of 3. We get, a factor of 6, a factor of 4. We are looking for 200 microamps. So this ratio will be 4. 50 microamps times 4 gives us 200 microamps as expected. Okay? All right, so you can see that we can extend this to as many current sources as we want. And the idea is that this diode connected device generates a magical gate source voltage. And that magical gate source voltage, when applied to these other MOSFETs, creates a current that has this simple relationship with the original reference current. Okay, that's great. All right. Now, we arrived at this topology by thinking that I have a current injected into a diode-connected device. It generates a VGS, and then this VGS goes to a destination device, and that's how we copy the current. But there's another way of thinking about it. So let's talk about this perspective. So alternative perspective. Okay, so I want to show you from a different point of view why this result makes sense, why this result should hold. All right, so here's how it goes. Okay, we draw our standard current meter like this. We have IREF here, and we have the other transistor also in saturation, so M1, M2. Okay, now both of these are in saturation, so they follow our standard saturation current equation for the MOSFET, which I had on the previous slide. Okay, so let's write these out. We have ID1 is equal to 1/2 mu n C ox W over L of 1. Each transistor can have an independent W over L, right? So W could be 5 microns, L could be 0.2 microns, whatever we want. All right, times VGS minus VTH squared. So we know that this transistor carries a certain current. It is in saturation, as we saw last time, because the gate and the drain are connected. So it follows this equation. VGS is this VGS, the voltage that we have between here and ground. Okay, how about M2? Same principle. So ID2 is equal to 1/2 mu n. The mobilities are the same if the transistors come from the same batch or they are on the same chip or on the same wafer. So mu n C ox W over L of 2, because this has its own dimensions. And then the same VGS minus VTH. We're also assuming that they have the same threshold voltage. So we see that they have the same VGS because the gates are shorted and the sources are shorted, so they have the same VGS. Okay, so what does this tell us? This tells us that ID2 over ID1 is equal to, everything cancels out, right? The only thing that's left over is this. So it's W over L of 2, W over L of 1. Okay, so it makes sense. It makes sense that the currents have to be related by the ratio of these W over L's, simply because the VGSs are the same, all these factors are the same, so when we divide them, we get this, right? That's another way of thinking about current mirrors. Okay. All right, so based on this, now we can go and look at another example. So here's another example. I'm going to build a current meter like this. So again, the current goes to a diode connected device to generate a certain VGS. So that's M1, this is IREF. And now I will copy this current onto something like this, and then another one like this, and then I short these two together and go like this. And we'll call this M2, we'll call this M3, and we'll call this I out. Okay, so the purpose of this problem is to determine I out from what we have here. Okay, so it's not that hard, right? Because we know how much current M2 has, like before, like here, like here. We know how much current M3 has, again, like here, right? So all we need to do is add the current of M2 and the current of M3 because their drains are shorted together. Again, we're assuming that all three transistors are in saturation. Okay, so then I can write I out equals the current of M2, which would be IREF times W over L. I'm going to write it like this because I don't have much room. W over L of 2 over W over L of 1. Right, based on what we have here. Plus the current of M3, which would follow the same idea. So we have IREF, and then we have W over L of 3 over W over L of 1. Okay, all right, so that's pretty good. Now, for example, if M3 and M2 are identical, and they are also identical to M1, so all of these W over L's are the same, then this current is the same as IREF, this current is the same as IREF, this current is twice IREF. Okay, so that's one way of building a current that is twice IREF, right? So previously, we just thought what we could do is make, for example, this transistor twice as wide as this transistor and use the same length. That would double IREF, right, when you copy it over here. Alternatively, we can assume that we have two transistors, we call them in parallel because the gates are shorted, the sources are shorted, the drains are shorted. So two parallel transistors that are identical, and they're identical to the original transistor, so this current is twice this current. Okay? It's really the same thing, this idea of using two devices in parallel versus making one device twice as wide. Okay? But this is another way of thinking about it. Okay, that's great. Let's go to the next page. And see what we need to do here. Okay, so I would like to talk about, I'm going to give you a quiz before we proceed. All right, so here's the situation. I have a current IREF. I'm injecting it into a device. And I would like to obtain a current equal to Iref over 2. We'll call this M1, we'll call this M2. Okay, so let's suppose that we have a dimension of W over L2 here, and this is fixed. So this is fixed. It's not under our control. And this is the minimum size. So this device has dimensions of W over L2. So let's say 2 microns over 0.2 microns. And we assume that we cannot build anything smaller than this. So W cannot be smaller than what this guy has. But at the same time, I would like to have a current of Iref here and a current of Iref over 2 here. So how exactly would I choose this device so that this current is half of this current? Okay, I'll give you 1 minute to think about that. Okay, so how do we choose the dimensions of M1? Well, what we know is that if we call this I2 is equal to W over L of 2 divided by W over L of 1 times Iref. And the question is, if this one is fixed, as we stipulated, how shall we choose this so that I2 is half of Iref? Well, naturally we will say that W over L of 1 should be twice W over L of 2. Okay, so for example, let's assume, as we will see, we do this all the time, L1 is equal to L2, and that means that W1 is equal to 2W2. Okay, so that's the proper choice. This device was wider than this device by a factor of 2, so that the current that this generates is half of the reference current. Okay, so that's good. Another possibility is this. Here's one transistor. And here's another transistor. We place 2 diode connected devices in parallel, each one having a certain W. So we'll call this W1 equals W2, W1 prime equals W2. We'll call this M1, we'll call this M1 prime, and then this goes to M2. And I claim that this current is also Iref over 2 if this is Iref. Okay? All right, so again, we're assuming that all the L's are the same, so L's are the same, and we're just playing with the W's. As a circuit designer, you have the ability to choose W and L in integrated circuit design. Okay, so why is that? Well, okay, so this guy has a width of W2. This guy has the same W, and this guy has the same W. Well, if I have two diode connected devices in parallel, I can try to redraw them like this. So this is M1, this is M1 prime. Are these the same thing as these? This line runs through the transistor. It looks a little strange, but that's okay. This is just for convenience, okay? It doesn't mean that it goes anywhere in here. All it means is that this gate and this gate are connected, just the way this gate and this gate are connected. After all, these are in parallel, so the drains are shorted, the sources are shorted, and the gates are shorted. So I just shorted the gates together, the drains together, the sources together. So we have two transistors that are identical, and they have the drains are shorted, the gates are shorted, and sources are shorted. This transistor is indistinguishable from a single transistor. So if we have W1 and plus W1 prime, W1 and W1 prime, this would be the same as that, except that it has the same width. So when we place two transistors in parallel, it is as if we had one transistor whose width is equal to the sum of the widths of these two transistors, provided that they all have the same length and the same threshold voltage. Okay, so we see that in fact this is like having 2W here, and that goes back to what we said before, right? We said make the diode connected device twice as wide as the destination transistor, and that's what we did. When you place these in parallel, it is as if you had one transistor who is twice as wide as a single transistor, or twice as wide as this. Okay, so that's how we copy to get a fraction of IREF, right? Not a multiple of IREF. All right, the next topic is proper scaling of devices in a current mirror. And that just goes back to what we have seen so far. So again, let's suppose that I have a diode connected device here with IREF, and I would like to copy this over to one here, and again I'm going to run this line through it, another one here. So I want to have I2 here, I3 here. Okay? All right, so what we do is always choose the same L for all of these transistors. Okay, we won't go through the details of why that is necessary, where does it come from, but for these currents to have good copying ability, to make sure that when we think this is, for example, twice this, it actually turns out to be twice that, and there won't be significant errors, we need to follow the same L for all of these. So these all have the same length. So the only parameter that we scale is W. So only scale W. Okay, so for example, again, let's call this M1, M2, M3. So we see that W2 times IREF, W2 over W1 times IREF gives us I2. So I know how much I2 I need, and I have chosen a certain W1. So I will go ahead and choose W2, according to this ratio to get what I need. So for example, if I want to triple Iref, this has to be 3, so W2 will be 3 times W1. The lengths will all be the same. And similarly, I will choose W3 over W1 times Iref to be I3. So if I need a certain amount of current for I3, and I know Iref, and I know W1, I pick W3 according to this ratio. So this is the proper way of scaling transistors in a current meter to make sure that I2 and I3 are almost as good, as constant, and as supply and temperature independent as Iref. Very well. Okay. Let's see. Now that we have seen these, we can extend these ideas to PMOS current meters. The idea is very simple, right? Similar. So let's talk about PMOS current meters and see how they come about. So this happens too. For example, if you build a common source amplifier with an NMOS input transistor, so here's a common source amplifier with an NMOS input transistor, Vin, and now we want to have a current source as the load. That current source goes from VDD to this node, so it has to be a P-type current source. So that is a PMOS device with a bias. So our objective is to see how we can provide biasing this gate voltage for this PMOS device so that its current is well defined and constant and all the good stuff that we talked about last time. Okay, all right, so the same idea applies. This VB has to come from a diode connected PMOS device that receives a reference current. So here's a diode connected PMOS device. The gate and the source are connected. The gate and the drain are connected. The source is up here. We draw the source up here because it has a more positive voltage than the gate and the drain. And that goes to VDD. So here's VDD. Now we need to inject a current to this device so that it creates the right amount of VGS. We did this here, right? We injected this current to create the right amount of VGS and all over the place. Okay, so I need to inject a current. And this current is going from this node to ground. So here's a current that we draw from this device to generate the right amount of VGS. Now we take this VGS and give it to our destination transistor, like this guy. So that goes here, and that will be the current source that we want. If I have many of these stages, they can all feed from this VGS. This VGS can go to this one, and the next one, and the next one, just the way we had these copies, right? So, for example, here we copied this VGS to this one, and so on. Okay, so that becomes a PMOS current meter. So this is our reference current, and we have taken this reference current and copied over to this one and perhaps some more. That current source can serve as a load for a common source amplifier, or it can serve in many other places, as we will see later. Okay, so that's great. We have the PMOS current meters in this topology, and again, if you want to be precise with respect to values that we have, this PMOS device will provide a current in this direction, and we'll call that, for example, I2, and I2 will be again based on the dimensions that we had, right? Based on the original dimensions that we wrote for these devices. So this will be W over L of 2 divided by W over L of 1 times Iref. And that is the amount of current that we create by copying Iref over here. Okay, so this is interesting. We can see that, again, our practice will be that we use the same length for these transistors, and we simply scale the current by choosing proper W's. So we have a W here and a W here. So for example, if the current of this PMOS current source must be twice Iref, then I simply choose W2 to be twice W1. And they will have the same length as we stipulated before. All right, so that becomes a very simple topology. Okay, all right. So let's look at an example here, just to play with these ideas a little more. So we go over here, and so here's an example. An NMOS common source stage requires a load current source equal to 200 microamps. Okay, so we have common source stage, has an NMOS input, there's a PMOS current source on top, and it has to be 200 microamps. We have a reference current equal to 400 microamps. So our objective is to design a current meter that can take 400 microamps and give us 200 microamps. Okay, all right, so here's how it goes. We have a reference current going to ground equal to 400 microamps. We inject this into a diode connected PMOS device. So here's a diode connected PMOS device, and that is copied over to the destination. So this is the current source that is supposed to deliver 200 microamps, and that is connected to a common source amplifier, V in and V out. Okay, all right. All right, so we call this M1, we call this M2, and what we know is that to ratio the current by a factor of 0.5, I will need to choose W2 to be half of W1, and the same length for the two transistors. So I will choose L1 equals L2, and then I will choose W2 to be equals to 0.5 W1. Okay? In practice, what we do is we actually go the other way, so we pick W1 to be equal to 2W2. This may seem the same thing, right? But it's actually a little different because what we'll do is we want W2 to be twice as wide as M2. And for that reason, WM1 will consist of 2 unit transistors in parallel. So the actual circuit will look like this. So these are diode connected devices, and they go here, and the reference is injected here. So each of these we will call a unit device. So we have 2 unit devices, in fact 3 unit devices. So unit devices. And that means that they all have the same W and same L. Okay? So this has a W over L, let's say 4 microns over 0.1 micron. This is also 4 microns over 0.1 micron. And this is also 4 microns over 0.1 micron. Now we took 2 units and configured them as a diode connected device. So equivalently, this device has twice the width of this device and the same length. So we have satisfied this, so the current is copied over with a fractional ratio of 0.5. Okay, so in practice, that's how these circuits are designed to make sure that the current that we generate here, and we believe is 200 microamps, it will be a pretty accurate 200 microamps, and it will inherit all the good features of this current source. Right? This is temperature independent, supply independent, and so forth. So we have to follow this practice to make sure that that happens. Okay, all right. Let us carry on with bipolar current meters. So the idea is very similar. So what we do is we take a reference current, Iref, and inject it into a diode connected bipolar device. So here's a diode connected bipolar device to generate the right amount of base emitter voltage. And then we give this to all the other destination current sources that we want to copy from here. Okay, so this goes to another bipolar transistor, and the current that is generated here has a certain ratio with respect to that current. Now, how do we write that out? Okay, so we have to remember that the collector current of a bipolar transistor is given by a factor which we call saturation current, IS. It's a small value times exponential of the base emitter voltage divided by VT. VT is KT over Q. It's approximately 26 millivolts at the room temperature. Okay, I have neglected early effect here, so I'm assuming that the current is independent of the collector emitter voltage, and of course both of these devices must operate in the forward active region. Okay, so if I have that for both Q1 and Q2, then I can readily find the relationship between I1 and Iref, right? They have the same base emitter voltage because the bases are shorted and so are the emitters. So I can say this is IC1, well, let's call this I2. IC1 is the current flowing through this, which is the same as Iref, and I'll give an index of IS1. IS1 is the saturation current of Q1. It's some factor that when you build Q1, when you buy Q1, it has a certain IS1. Similarly for Q2, we have IC2 is equal to IS2 exp VBE over VT. They have the same base emitter voltage, so this cancels out. We can say that IC2 over IC1, meaning this current over this current, is given by IS2 over IS1. So for example, if Q1 and Q2 are identical, then their saturation currents are identical. So the current that we generate here is equal to Iref. All right, so that's the principle of copying or current meters in bipolar technology. It's very similar to the NMOS counterpart or the PMOS counterpart. All right, so There is one little difference that we need to remember, and that is the following. So I'm going to use different color just to highlight that. This transistor has a base current, and so does this. So these are base currents that the transistors draw, and these base currents have to come from IRF. You see, IRF comes down. Most of it flows through Q1, but we lose some of it this way, because this has to provide the base current for Q1 and the base current for Q2. So the current that actually flows through Q1 is not exactly equal to IRF, which means this one is not exactly IRF, which means IC2 is not exactly equal to this ratio times IRF. It's a little smaller. And that's something that we need to keep in mind. There are methods of alleviating this problem, but we will not go there. Okay? You just remember that there is a base current, and we lose some base current here and some base current here. That's the difference. Okay. All right. I would like to leave you with a problem, and then I'll talk about this problem. I'll solve it next time. So here's a problem for you to think about. Suppose I have a reference current source that goes to ground and is IRF. Okay, it's a golden current source, nice and constant. And I have a source follower that needs to be biased. So this is V in, this is V out. Okay, so this current source needs to be a copy of this current source. How exactly do we do that? You see, this side of the current source is grounded. It's hardwired. We cannot change this. So how exactly do I take the information from here and give it to this gate so that this current I1 or I2 is a good copy of IRF? Okay, so I will you think about this. I'll see you next time.